Find what it means for a sequence of functions to converge uniformly to a limit. What we are going to do in this video is basically continue to explore implications of those definitions. Okay, so our first result basically says that if you have a sequence of a sequence of functions that converges uniformly to a certain limit, then you can do a certain interchange between a limit and an integral. So let me write this formally down. So the statement of the theorem is as follows. Let Fn be a sequence of continuous functions on, say, a closed interval AB, converging uniformly to F. Then the following is true. Limit n tends to infinity of the integral from a to b of fn of x is in fact equal to the integral of the limit. Okay, so therefore if you stare at the statement, it looks like what you have done is basically interchanged the limit and the integral, or rather you have pushed the limit into the integral, right, such that the limit of the integral of fn of x is in fact the integral of f of x. Now we haven't formally defined the integral yet, but nonetheless to prove this we won't need many of those properties, so still we're going to go ahead and kind of prove this result. Okay, so I will just tell you the properties of the integral that we need, and then we will formalize these next week or so when we get to actually studying integration formally. So the first thing to note here is that the function f is continuous, right, because it is the limit from the uniform convergence of a sequence of continuous functions. So we know that the uniform limit of a sequence of continuous functions is in fact continuous, right? Moreover, as it should be for the statement to hold, all continuous functions are integrable. This is something we'll prove formally next week. Continuous functions are integrable. Alright, so now let's go through the proof. The proof is going to be remarkably straightforward. This is going to be a trivial almost consequence of the notion of uniform convergence, right? So given some epsilon greater than 0, there exists capital N such that fn of x minus f of x in absolute value is less than epsilon by b minus a for all x in AB and n greater than capital N. Okay, now since the absolute value of the difference between fn of x and f of x is uniformly upper bounded by epsilon by b minus a, then we may upper bound the integral difference as follows. So in other words, if you look at the integral from a to b of right, so I want to look at the absolute value of the difference between the integrals of fn of x and f of x. Now this can first be upper bounded by the integral of the absolute value. This is a property that we will again have to prove, but it should be natural that this holds, right? Alright, and once you have this, we know that this is upper bounded by epsilon by b minus a, and so therefore the overall integral is also upper bounded by epsilon. Right, and so therefore what we have shown is essentially that the limit as n tends to infinity of the integral of fn of x minus f of x is equal to 0, right? Because for any epsilon we have shown that in absolute value this integral is in fact going to be less than epsilon for n large enough, right? So that's what we wanted to prove. So moral of the story, when you have a sequence of continuous functions which converge uniformly to a certain limit, in that case the limit of the integral along the sequence is in fact going to match the limit of the integral of the limit. All right. So now, having proved this statement, we are now going to define the notion just a moment. Yeah, we are going to define the notion of what it means for a sequence of functions to be uniformly Cauchy. Right? So the definition is going to be quite natural given our prior experience with Cauchy sequences. A sequence of functions fn of x on S, which is a subset of R, is uniformly Cauchy on S if the following condition is true. For any epsilon greater than 0, there exists some capital N such that the difference between fn of x and fm of x is going to be less than epsilon for all m and n larger than capital N and for all x in S. Right? So this is the natural notion of uniformly Cauchy, because it tells you that whatever epsilon you choose, there exists some capital N such that beyond this capital N, any two functions in the sequence are going to be uniformly bounded away from one another by at most epsilon. Right? So that is what it means for a sequence of functions to be uniformly Cauchy. Now you should expect that uniform convergence in fact implies uniform Cauchy. So this I'm going to just state as a lemma and leave the proof as an exercise to you, that if fn tends to f uniformly, then the sequence fn is uniformly Cauchy. Right? This should be quite easy to prove, because after all, if fn is going to be uniformly bounded around f, right, that means that beyond a certain point the elements of the sequence must also in fact be uniformly bounded from each other, very analogously the way you show that a Cauchy sequence is also a convergent sequence is a Cauchy sequence. Okay, so this is straightforward. The opposite is what we will prove, the converse, namely that uniformly Cauchy sequences are in fact also uniformly convergent. So that is what we will instead prove here. So let fn be a sequence of uniformly Cauchy functions on, again, S, which is some subset of R. Then there exists a function f right? So between between the lemma and the theorem, what we are basically showing is that uniformly convergent is equivalent to uniformly Cauchy for real valued functions, right? If a sequence of functions converges uniformly, then it's also uniformly Cauchy. That's easy. What we will now prove is that if a sequence is uniformly Cauchy, then it is in fact also uniformly convergent, right? Namely, a limit exists such that Fn converges to F uniformly. All right, so here is the proof. Now, what we are given here is that the sequence Fn is a sequence of uniformly Cauchy functions, right? Right. So now for any x naught in S, check that in fact Fn of x naught is a Cauchy sequence in R. Right? And since R is complete, we know that there exists a limit, right? This means so let f of x naught denote the limit. Right? So having constructed this f, right, such that at x naught it is in fact the limit of the sequence fn of x naught, we can therefore conclude that fn in fact converges to f pointwise. Right? And as we've talked about before, this is therefore that makes f the only potential candidate to check uniform convergence for. Right? So how do you show that you have uniform convergence? Well, thus there exists an n in the natural numbers such that fn of x minus fm of x is less than epsilon by 2 in absolute value for all x in S and m and n greater than capital N. This is in fact a direct consequence of the definition of uniformly Cauchy. Now, in the inequality above, take the limit as m goes off to infinity. Right? As m goes to infinity, we know that fm of x will in fact converge to f of x. So therefore, you should be able to conclude that fn of x minus f of x is less than or equal to epsilon by 2, once again, for all x in S and n greater than capital N. Right? And since it's upper bounded by epsilon by 2, it can of course be upper bounded by epsilon. Alright, so this in fact shows that the sequence is uniformly convergent, right? Because we have uniformly bounded the deviation between fn of x and f of x for large enough n. Okay, so this is all it takes to show that uniformly Cauchy implies uniformly convergent. Okay, so we'll stop here. What we have to talk about next is to look at a series of functions and apply the ideas that we have developed already for sequences of functions to series of functions.